With that, let's get started with some introductions. As I said, I'm Mike Bolick. I handle marketing for CloudSearch. Joining me today is John Handler. John's a solutions architect for CloudSearch. He's an experienced search engineer and developer, and currently spends his time working with a bunch of customers implementing CloudSearch. So welcome, John.
Good morning, everybody. Welcome.
Our special guest today is Paul Nelson, CTO of Search Technologies, one of the world's largest providers of search consulting and implementation services, and they're part of the AWS partner network as well. Paul's worked on search for a long time, over 20 years, and he was the architect of Retrievalware, which many of you may know, and it was later acquired by Microsoft. He's worked with thousands of customers and has been involved in hundreds of search installations of all shapes and sizes. So he's got lots of experience and unique insights to share with us today. Thanks for joining us, Paul. Paul, thanks for joining us.
Oh, hey, everybody. Sorry about that. Pleasure to be here.
A couple of housekeeping items. You will see some polling questions pop up, so please enter your responses, and we'll review the results after 10 or 15 seconds. As I mentioned, Q&A will be at the end, about 40 minutes from now. So send us your questions as we go along. We will be recording this webinar. You'll get an email with a link to the recording within a day or two, and in addition, we'll post the slides and a recording. So you'll see the recording on YouTube and the AWS channel, and you'll be able to access the slides on SlideShare. A quick look at our agenda for today. We'll start off with a summary of Amazon CloudSearch to ensure that everybody's up to speed on what it is and what it does. Then Paul will take us through the steps he took to add improved search capabilities for the Wikipedia data set, working from the data acquisition and cleanup to building the index, improving the relevancy and the ranking of results, and building the user interface. And finally, we will wrap up with some recommendations for your search implementations and move to the Q&A portion. So what is Amazon CloudSearch? Here's the summary. It's a fully managed and fully featured search service that runs in the AWS cloud. So you no longer have to worry about setting up, maintaining, scaling, and operating your own search platform. CloudSearch has a unique capability to scale automatically as your data or traffic fluctuate. So resources are added or removed dynamically to meet the needs of your application. CloudSearch can handle structured and unstructured data, and it supports near real-time indexing of your documents, so you can quickly search for documents after they've been uploaded. It's designed to be up and running in less than an hour. We see many customers get up and running very, very quickly. So you simply upload your data, configure your search domain, and then CloudSearch takes care of the rest in terms of your indexing and provisioning of all the technology and hardware required. And finally, you pay only for the resources that you use, and the costs start at less than $100 per month. So let's turn to our first polling question. I'll just bring it up now. And we're going to ask you, what search are you using today? So select one of the following. You're not using any search today, or you're using a database, relational or NoSQL database. You may be using open source search such as Solr or Elasticsearch, or you're using a legacy enterprise search vendor such as Endeca or Autonomy, or you're using one of the Google products, Google Search Appliance or Site Search. Okay, just a few more seconds and we'll close the poll here. So if you could enter your results, that'd be great.
I like this slide because it's practically a history of search right in front of us. I can remember the old days when I tried to explain what search was, and people asked me, "Oh, so that's a relational database?" And I'm like, "No,
right."
Not quite.
But let's take a look at the results. I think they're interesting, Paul. So right now we can see there's still some people not using search out there. So 9% of you are not using search, about 15% still on database. Open source continues to be popular, 54%, and then we see 29% stuck in the legacy world. and 21% are using Google products. Now, of course, since CloudSearch launched 3 months ago, there are many customers already in production, so we anticipate seeing these numbers change over time. So let's move on, and Paul, maybe you could get us started.
Sure.
I'll just advance the slide for you, Paul.
And will you make me presenter?
Yep, just 1 second.
Okay. Yeah, it's interesting. I mean, obviously the AWS environment is very closely tied to the open source environment. And so, it certainly makes sense that the open source environment is going to be the primary search engine used by the developers today. So, Mike, do you need to close the? Oh, there we go. Show my. Excellent. Well, welcome everybody. I think this is just a fantastic opportunity to talk about Wikipedia and searching Wikipedia. We had a lot of fun doing this project, and we've had a lot of fun working with the Amazon team, and it's great to talk about it. I think it's a good demonstration of CloudSearch and what it can do. So, when we first heard about CloudSearch, we were like, oh, this is fantastic, and we wanted something that would really stress CloudSearch a little bit and really test all of its features and kind of a platform that we could use to experiment. I mean, we could have thrown random data at it, but we thought, let's use Wikipedia. I mean, after all, it's awesome, right? I mean, I use it at least 100 times a day. And as everybody knows, the default Wikipedia search is really bad. I mean, lookup is good. If you want to find a particular article based on the name, that's really good. But search is really bad. And we'll just see it later. And it's publicly available data, right? So I can just download the dump files and index them. Well, I mean, I say, we'll talk about the steps that it took to do that. And then it's awesome. And I put it's awesome twice because it's twice as awesome. Cool. So now why CloudSearch for Wikipedia? Well, I mean, we were really excited about the possibility of CloudSearch because we know how difficult it is for lots of our customers just to provision a search engine. So that part of it is just awesome. We think it's a really great choice for a public serving search engine. I mean, it lives on the internet, just like Wikipedia, so shouldn't we be using a search engine on the internet like Wikipedia itself? We got the first version up and running really quickly, and then we went through, oh gosh, at least 13 different iterations to tune it all exactly the way that we wanted. It automatically scales to the required query volume. I think this is critically important for something like what we wanted to do, because we had no idea how many people were going to be doing searches on Wikipedia. I mean, it could have been this viral sensation that went across the web, and then we could have seen this huge spike in our query requests. So to not have to worry about that is such a relief. So if there's this big viral spike in queries, CloudSearch will just magically handle it all, and there won't ever be a problem. So you never know with a public-facing search engine exactly what you're going to need, and that's just worked out great. Turns out the rank expressions for the Wikipedia data worked out really well for CloudSearch. And then I just wanted to point out that during the process of creating our system, this is not exactly about Wikipedia, but during the process of creating our search engine, we found that the way that you can create search domains in CloudSearch, because you can create a search domain very easily, it actually led us to a new way of developing an application, because we have the user interface team working on an old version of the index, while the indexing team is working on the next iteration, the next generation of the index, and it just made the actual development so much easier, so much faster, so much more stable. So that was an unexpected bonus. So let's go ahead and give it a shot. I'm going to go ahead and close up my window here. So this is the standard Wikipedia search. And so we'll search for Amazon, because after all, that's what we're doing. And just taking a look at the standard search, I mean, it feels so 1990s, actually. All you get is a title, a very short summary, some useless information, like the date information, which is really not that helpful. I'll explain why. The size, I'm not sure that people really care much about the size. You don't really know what types of documents these are. You don't know what categories. There's no opportunity for exploration. And then you have this really weird navigator at the bottom. We just felt that this kind of search engine was just so limiting and that we felt we could really do a lot better. So let's go ahead and take a look at the new Wikipedia search engine. We'll execute the same search. And here we go. So this is the Wikipedia user interface search engine that we put together with CloudSearch underneath. As you can see, the presentation itself is a lot nicer. Just the presentation of each of the individual articles. We have a nice summary of the article, which we call a static teaser. We can tell you what the type of the article is. You see that the first one is an article and the second one is a disambiguation page. You get links to the author. The last updated date is a little more useful. And then you get a list of all the categories contained inside the article, which is a really fun feature for doing kind of an exploration of the Wikipedia database. On the left, we get navigators with the full navigator counts on the left. So you see these different article types. On the left, these are all Wikipedia namespaces. And then the different categories, which are categories extracted from the Wikipedia engine itself, with all of the exact counts from all of the categories. That's one of the key and really nice things about CloudSearch is that all the counts are exact. So the count here and all the category counts and everything is exactly what they should be. The authors, we actually thought the authors would be more useful than they turned out to be, just because there's a lot of robots happening, and so you mostly get authors who are robots. And similarly with the last updated, because you have so many robots running around, almost always 2012 is by far the strongest. The user interface framework that we use has the possibility for doing charting. So we can see a chart of the different page types here, which is really fun. Most of them are articles, of course. Wikipedia pages are about Wikipedia themselves. The updates timeline, again, you can see most of the updates occur in 2012, which is typical because you have so many robots. And then the top authors. And again, most of the top authors are robots. But if you want one of these, let's click on Graham Hardy, just because that's kind of fun. And so here we have all the articles by Graham Hardy that he wrote in the files that he uploaded. We can go take a look at that author, Graham Hardy, My Life So Far. That's nice. And I had mentioned about the ability to do exploration. One of the things that I really liked is I said, oh, well, let's find American films that mention Amazon. And so, oh, well, that's kind of cool. How about Tarzan films? Tarzan and the Amazon. So let's remove the word Amazon. Let's remove the American films. And now we have all Tarzan films, which I just think is really fun. And so in this way, you can kind of do this kind of an exploration of the database. And it's just you just discover all kinds of really fun things about Wikipedia that you didn't know, and areas to research and just fun things. I find myself just sitting in here for a while, just kind of playing and seeing what comes up. So that's the goal. In order to achieve that goal, we went through a particular process. This is the sort of process that most people will go through for most certain. Some of the steps may be very small and very easy, and other of the steps may be larger, more complicated. So we're going to go through each of those steps and how we did that for Wikipedia. The first step was data acquisition. And data acquisition is fairly straightforward. In Wikipedia, we have this list of dump files. It's essentially an FTP listing. And the files that we want are all of these enwiki latest pages articles xml.bz2. There's 27 of them, and they are all bzip2 compressed slices of the Wikipedia pages. Now, there's a lot of different ways that you can go about fetching the data, right? You can just use a Perl script, for example. If you have your data in a relational database, then you might use a regular export tool or an ETIL process. What we decided to do was to use a framework which we have called Aspire for doing the content processing. It's a Java pipelining framework which you can actually download and use yourself if you go to the Search Technologies website. The way it worked for Wikipedia is we first fetched the listing. That is, we fetched the HTML page, which is the list of all the files. We then scan through that to identify the files that we actually contain the dumps that we need to process. We did that with a regular expression matching. It's a little more complicated because there are multiple versions of some of the files, and so we have to actually gather up all those versions, sort by date, and choose the latest. Once we have the list of files identified, we're going to now open a stream against each one of those files and pipe that data down from Wikipedia. You can open 2 connections to Wikipedia at a time. That allows you to do a little parallel processing. And then the stream is then sent through file processing, which we'll talk about later. And the end result of file processing, of course, is a series of individual records that get sent to Amazon CloudSearch. Just some advantages of this content processing framework over, say, a Perl script or some kind of other more ad hoc approach is we can process multiple files simultaneously. Everything is fully streaming, so we never actually download the data to local disk. We just stream it straight from Wikipedia through a streaming processor and straight out to CloudSearch. So that's kind of cool. And it's fast. I was really surprised. You know, we started, and as we worked on it a little bit, we were able to get up to 450 documents per second end-to-end, which is practically a home run, which is just to say that CloudSearch can accept documents very, very quickly. And remember, this was end-to-end all the way from Wikipedia through all the processing and out to CloudSearch. That's a really good number. Most other, vendor systems I would use are probably in the 50 to 100 range. Integrated connectors, if you have other sources that you need to crawl from, like SharePoint or websites, it has text extraction built in. We use Apache Tika for that. And then some entity extraction as well for names, places, companies, and so on. So we're all ready for the next polling question. Curious to know where your data is stored. We tend to take a data-centric approach to search, and so almost always the very first question we ask everybody is, where is your data and what's it like? Do you want to take over, Mike?
Yeah, just 1 minute and I'll open up the polling question. So here, the question is, where are you keeping your data? And please select one of the following: the file systems, S3, database, CMS, or some other type of repository.
It's a useful question. I think you know that CloudSearch can index documents straight from S3. And so that's a useful feature of CloudSearch. File systems you can do to some extent with command line tools. Relational databases and other content management systems can be a little trickier.
Okay, well, let's take a look at the results, Paul. So 44% in file system. Yeah, database, big time, 70%. Although this was a multiple choice question, so S3 is obviously pretty popular. Still a lot of CMS data out there, and there's other repositories, the 19% for other.
Okay, so this seems pretty typical. A lot of our customers have databases. I mean, that's a very common storage structure, especially these days. You may, for example, want to simply export your records and then do some kind of XML transformation to transform them into CloudSearch documents. That's certainly possible. Or create a framework like ours, or use the Search Technologies framework, which has components for accessing relational database data. Okay, so we have acquired the data from its originating location. We're now ready to do data processing. I think this is one of those steps that a lot of people discount. People who are not in the search world, they tend to think that, I just take my fields from wherever they are and write them to the search engine. But oftentimes you need to do some sort of processing, field mapping, field adjustment, value normalization, so that you get good results for the end user. What we did for the Wikipedia, well, let's first take a look at the Wikipedia data. This is what the Wikipedia XML file looks like. This is one of those, a sample of one of those XML files. Every one of the XML files starts with site info, which is about the site itself, and then you can see it has page, 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 page. Now, each one of those pages will be a page that we want to index as a separate record inside of CloudSearch. And you can see the title, ID, timestamp, username, and then the actual content of the Wikipedia article as entered by the Wikipedian. I'm just trying to see if I could find there's a redirect. So here's an example of a redirect. It has the redirect flag set to it. These are redirects in Wikipedia that we don't want to index. So not all of the pages we necessarily want to send over. So somehow we want to convert each one of these into an individual add command to Wikipedia and process the fields as necessary. Now some of the things that we did for data processing, of course all the data is in bzip2 compression, so at a minimum we have to decompress that into a UTF-8 stream. Then we want to extract each of those individual pages from the larger XML document and send them to CloudSearch, who used a SAX parser to do that. We then skip the pound redirect pages, so we want to identify all the redirects and then just cancel those. And we do compute some document statistics, and we write those document statistics into CloudSearch fields, and that helps us for relevancy ranking. We'll talk a little bit about that later. And for some of the advanced features, the categories navigator, the authors navigator, the update dates, there's some additional processing. You notice that the updates date was just year month, so there's some date manipulation there. The document type, we extract the prefix of the title for the document type. Disambiguation pages turns out to be really complicated. It's based on certain templates that are used on the page, and you have to have both a template whitelist and a template blacklist before you can accurately determine what pages are disambiguation pages and which ones are not. So there was a whole slew of iteration that was required around that. And then finally, and it has this large info box at the top, and it's got all of this extra encoding, kind of ugly encoding embedded, and HTML comments and all kinds of other junk in there. When we take a look at the after picture, we see something that's a lot cleaner, a lot nicer, a lot more readable. And that's what the static teaser processing required. Not all systems require this. In fact, very few, but it's I think a good demonstration of the kind of processing you may have to do on your documents. Okay, so that's document processing. Let's move on to the next stage. This is indexing. This turns out to be one of the easier parts for CloudSearch. You just create the XML and pretty much it worked first time. So that was the about the sum of it. But there are a couple things that are worth communicating. One is every document needs to have a unique document ID, so that when you submit that same document again, CloudSearch will automatically understand that you're submitting an update instead of an add. So every document has a unique document ID. It has to have only letters and digits. So if you have something like a URL, you'll need to MD5 encode that. The document version. Now this is actually, it seems odd, but it's actually an incredibly powerful feature of CloudSearch. One of the things that we've always had a problem with is doing parallel processing across multiple incoming streams of data. And you have a situation with that happens across multiple threads or multiple processes where a newer version will take longer to process than an older version. Or I guess it's the other way around. A new version will take less time, and an older version will take a long time, and then the old version overwrites the new version. And so you have all this synchronization code you have to do, which is kind of a real pain. CloudSearch does that all for you, and it's a fabulous thing. It guarantees that every document with a lower version for that document than has been indexed previously is just ignored. So you never have to worry about this problem as long as you have that integer version number that increases for every new version of the document. Now in the case of the Wikipedia system, we just did large batch updates, right? We would just update everything and then do another batch update. So we just set the version number equal to the current system time of the initiation of the crawl, minus some very large number, and in seconds rather than in milliseconds. And so that's a good general purpose formula for you to use for document version, which is used by lots of people. Some of the details of the indexing, we formed all the fields into CloudSearch SDF. That meant, selecting individual fields and mapping them to SDF fields. We submitted it in batches. Submitting them individually versus submitting them in batches was responsible for like about an 8 times performance improvement. You can also open multiple connections to CloudSearch, which I think is really cool. You don't have to send it over one pipe. You could open up 5 pipes and send it across, 5 different connections to the CloudSearch system. You get some improvements there. And then finally, if you put your index, it's not the same zone, it's the same region as CloudSearch. So if your indexer is on an EC2 instance in the same region as CloudSearch, then you get many times better performance. We were surprised. We had this thing running just on my laptop, actually, and we were getting about 50 documents per second. And some of that was some of just my laptop, but we moved that to a large instance in the same region as the CloudSearch system, and we got 450 documents per second, so that was like a 9 times improvement. The bandwidth within a region is so large that putting your indexer within the same region as the CloudSearch search domain is just a big win. Here's an example of the CloudSearch SDF. CloudSearch SDF is just this XML record which represents a batch of transactions. And you can have both add and delete transactions. And so you see the add transaction there with the version number and the ID and the list of all the fields that were submitted along with the document. And you can see where some of the fields like year, month have been carefully processed ahead of time, as well as the teaser, and some other content. Cool. Oh, and you see the title size and the content size. So those some other statistics that we compute as we go along. So this is an end-to-end of the data acquisition, data processing, and indexing data flow. We start by fetching that dump file. We extract the URLs that we want to index. We then open a stream on every URL. We bzip2 compress that stream. It's a streaming decompressor, so that's very cool. We then do an XML subjob extractor that underneath that uses SACs to extract the individual pages. Each individual page then goes through a metadata cleansing and content cleansing process, which we did with Groovy scripting. Our framework has a Groovy scripting module you can stick in there. Intermediate XML into Amazon CloudSearch XML, batch that up into batches, and send it to Amazon. Cool. All right. We have a couple more sections, and then we'll take questions. Queries and relevancy. This is, being a search guy from the 1989. Queries and relevancy has always been my #1 fascination. And obviously, there's a lot of different relevancy models, a lot of different ways of doing queries. What we started off with was this debug interface. And this is something that we do for almost, all implementations. I can send you a copy. It's just an HTML file. In this case, for CloudSearch, we actually hosted it on an EC2 instance with a little proxy server, just for fun, basically. And so I'm going to turn on the raw representation. It has an XSL. The hosted version has an XSLT transform, so I can submit it, and you can see it gives me the results here. Let's do another query. Amazon. Like so. Amazon, the Amazons. You see a lot of Wikipedia articles up top and categories. This is some of the relevancy ranking that I was talking about. You can see the raw XML by clicking on raw equals true here. And when I submit that, you now see the basic structure of the XML that comes back from CloudSearch. And so this is the XML that needs to be rendered into your user interface in some way or another. Here we have 4,000 hits. We started on hit 0. The match expression, the rank, it's sorting descending by text relevancy. And then within each of the hits, you have all of the individual hits, each one with a hit ID, and then the list of fields, which I selected, the multi-value categories field, the teaser, text relevance, some of these other items, content, size, resubmit. In addition to this hits tag, we now have a facets tag. And inside the facets tag, we have both of our facets, the author and the categories. Within the author, we have an individual constraint tag for each of the individual values with the counts for all of those. And then similarly for the categories tag. So it's a very straightforward XML structure, very easy to parse and turn into an XML presentation. And you see it also has the time, so it tells you how long it took to do the query, and the request ID. So that's just a very useful technique. And then you can play with different types of relevancy ranking, different types of parameters, play with the BQ queries and make sure that all of those filters are working correctly, and the debug interface really helps you do that. Now, queries for Wikipedia, turns out the query was quite easy for CloudSearch. We just take whatever the user entered and put it into the Q field. We use the BQ field for selecting facets, and the BQ, you can specify the field, the name, and the value, so it'd be like actually the word field and then title and the value. For including filtering on a facet and for excluding a facet value, because our user interface allows for both including and excluding facets, you have a not parameter. And you can combine these expressions with and or. The only comment I'd make about BQ and these prefix notation is just don't forget to escape the single quotes. So remember that you have single quotes in here, and if your data value has single quotes, you'll need to be careful to escape those. Now, relevancy ranking. Gosh, I could spend hours on this, but I won't. In CloudSearch, this is done with rank expressions. Now, rank expressions is a way of doing relevancy ranking that emphasizes document quality. That is, if you have any sorts of statistics which identify high-quality documents over low quality of documents, then rank expressions are going to be perfect for that. So as an example, any kind of document statistics like content size or title size or whatever, if you have ratings, if you're doing that kind of search engine, e-commerce will typically have a lot of good document quality data like sales data, ratings data, click-through counts, conversion counts, and things like that. If you have interlinkages, say you're doing an academic database with reference biographies, incoming links will be a very useful one. We wanted to do that for Wikipedia, we just didn't have the time. If you have editorial comments like flags or popularity, freshness and recency. So if you're like in a news system and you want your more recent documents to be of a higher quality, then you can incorporate that into the rank expression. Expressions are uber flexible, and they work great. I mean, you just specify the expression in the CloudSearch console, and then it'll create a rank expression that you can then use for sorting with the rank parameter. So it's very easy. In the case of Wikipedia, we decided to boost longer documents. That's because longer documents tend to be more comprehensive documents, which are more descriptive. And also documents with shorter titles. We discovered that once you had longer and longer titles, those documents tend to be about more niche areas rather than over broader areas. So for example, a query over Olympics will be just the smaller title of Olympics will be better than Olympics of 2010 swimming team from Australia, for example. And then we decided to reduce documents in the Wikipedia namespace. Documents in the Wikipedia namespace are about Wikipedia itself. They're not so much about articles that end users would most likely to see. And then this is the resulting expression that we came up with. We tend to use logarithms a lot just because most of this type of data is log normal data, and taking the log 10 of it will give you nice Gaussian distributions that you can use. Cool. Okay, so that's relevancy ranking with Wikipedia. And again, that was mostly just figuring out what the formula was and then entering it into the CloudSearch console. So very, very easy, actually. And then finally, building the user interface. Now, with the user interface, you can build it in a variety of different ways. Every toolkit that's known to man, Java server faces, or if you use a proxy server, you can get the JSON directly from CloudSearch and render it in jQuery or some other client-side application, for example. If you get XML from CloudSearch, you can use an XSLT transform to render it, which you saw in the debug interface. What we decided to do was use this search user interface framework called TwigKit. And it's useful because those guys have handled all of the detail work about how to render navigators and all of the clicks and all of the breadcrumbs and everything, so that most of that user interface that you saw was a TwigKit widgets that we then combined together to make our custom Wikipedia search engine. In order to get CloudSearch to work with TwigKit, though, we first created a Java API, and this is open source and was announced on the Amazon forums, which is just an ordinary Java API that handles all the communications to CloudSearch. That is, creating the URL and the parameters, and then processing the CloudSearch query XML that comes back. We then wrapped that Java API with the CloudSearch platform. That's a special TwigKit plugin, which essentially translates the communications required by TwigKit to the communications provided by the CloudSearch Java API. So it's a translation layer to translate between CloudSearch needs and TwigKit needs. Both of those turned out to be quite easy to create, and it was really quite easy. And then once we plugged the whole thing together, we got the beautiful TwigKit interface that you saw. And so just to emphasize the UI architecture, we have Tomcat for the Java application container, TwigKit, which handles all the graphical user interface controls, the CloudSearch platform translates between TwigKit and the CloudSearch Java API, and then finally the CloudSearch Java API, and there's a link for it if you'd like to download that, and source code is provided, so you can do whatever you'd like with that. And that's it. So let's just do a quick summary. These are the typical stages of a search engine implementation. Data acquisition. You can use a variety of different techniques. We used our own framework called Aspire. Data processing. Again, a variety of scripting techniques are possible there. Again, we used our own framework called Aspire. Indexing. Again, very straightforward. Just create the right XML structure and pipe it over to CloudSearch. Query. That's a question of identifying what query parameters, what query structure and rank expressions you need to use. And then finally, the user interface. And our solution for that was the TwigKit API, although, again, any other Java server faces or jQuery end user interface would work just as well. And there you go. Thank you so much for your time. I think we have plenty of time now for questions. Mike, would you like to take over?
Sure. So if you haven't entered in your question, please do so in the question box on your GoToMeeting control panel. Paul, I think you addressed this, but I have one question here, which was, what did you use for category extraction?
Oh, right, the category extraction. That was a simple regular expression over the content. Categories are identified in the content with square bracket, the word category, a colon, and then the category. So we ran a regular expression to extract all of those, and then we did a little normalization on the category name itself. And then that gave us a list of categories, which we then, of course, put in as a list of field tags in the CloudSearch STF.
Great, thanks. So John, I guess this one might be for you. And Paul, please chime in. The question is, how easy is it to move from Solr, let's say, to CloudSearch?
Yeah, thanks. So it's really simple to move from Solr to CloudSearch. You have, on one hand, the getting your data into CloudSearch, and CloudSearch is format is very similar to Solar's format. So you can intercept very easily your Solar documents and send them over to CloudSearch. And we support a range of features that Solar supports, and should be a quick step over.
I might add that we've already had a number of users that have done the migration with really very little pain. Yeah.
Yeah, I think that the index XML structure, the update XML for Solar is almost exactly the same as the update XML for CloudSearch, so that's a very easy translation. And the parameters are roughly equal.
Then the CloudSearch deployment, what did that look like in terms of the number of instances?
The wiki, it kind of went all over the map, but when we finally got everything cleaned up and all the redirects removed, we ended up with about 6.7 million documents in the Wikipedia database. Now I know if you go to the Wikipedia homepage, it says there's like 2.8 million articles, but not every page is counted as an article for that count. So the total number of pages minus redirects, that includes Wikipedia pages and pages which are too small to be considered to be articles, came out extra large instances, and that I think is in part because of both the traffic and the data size.
Yeah, let me just piggyback on that a little bit. CloudSearch, as Mike mentioned at the beginning, does automatically scale in two directions to handle your search problems. So as you send more data, CloudSearch will scale from a small to a large to an extra large, and then partition out to handle as much data as you want to send. And it also, as you send more traffic, we will add copies or replicas of each of the partitions to handle additional traffic as you're sending it to us. And then, of course, if traffic dies down, if you're dealing with a spike or something like that, we'll scale back to right-size the domain to handle your traffic. And, as of now, we have some limits on size that you can scale to, which is 10 wide and 5 deep. But it's very easy. We have a little form on the website. You can contact us. We can expand that pretty much as large as you'd want. We currently have customers with more than 1 billion documents and more than 1 terabyte of source data. So CloudSearch can scale to be quite large, and yes.
And that would be a terabyte of post-processed data, I imagine, whereas a lot of people, if they're indexing PowerPoint presentations and Microsoft Word documents, that can run up into the terabytes really, really quickly. But I think what you're talking about is the post-processed data.
Yes, exactly, and that's an excellent point. We hear from people who say, I have 50 megabyte PDF files, and how am I going to get those in there? And really, when the text is extracted from that file, it's going to be quite a bit smaller than that.
Okay. Hey, here's one question. How can I search domains based on document types? Could be blogs or images or videos. The question was, how do I query across all of these domains? You want to take that, John?
Sure, I'll jump in. So one thing is that thinking about your search problem and your data layout, you can actually segment your data within a single domain by adding a type field to each of your documents and then using that as a filter within your queries. So within a single domain, you could put different types of corpus or different sources of information. To search across domains is a somewhat complicated problem where you would have to send each of the queries and then do some kind of federated search that includes a blending of the results keeping in mind the relevance values in each of the different domains to get an overall sort. Another way to approach it is if the types of information are very different, then to present different segments in the user interface representing each of the sets of results from each of the types of information.
Yeah, I'll just make a add that we recommend if you can put everything in the same search domain, you will get the best possible relevancy ranking from doing that. It'll share the statistics and have a better more uniform text relevancy across all of your documents if you can do that. And if not, then I think just sending out parallel queries and presenting those in multiple tabs or multiple divs is maybe the best way to go.
Thanks, Paul. So here's a question that just came in around how do you handle different users having different access to data based on their own data and connections to other users, such as Social Graph?
Mm-hmm. CloudSearch's security model is IP-based at the moment. So if you were talking about securing the domain itself for access from different groups of people, we don't currently have a great solution for that. Within a CloudSearch domain, you can add access information to each of your documents and then use Boolean queries to restrict access based on the querying individual. Actually, I think Paul can probably comment on that too.
Yeah, and I mean that's almost exactly what's done. As you crawl the documents, you extract the ACLs and then index the ACLs into an ACL field. And then when the user connects up to the system, you'll expand that user to all their group membership and create an OR of all the groups to which the user is a member of. You may also have a not ACLs field if they're deny ACLs as well, and then construct the appropriate Boolean expression. The Aspire framework that I mentioned does have connectors that actually extract all those ACLs and then index those into CloudSearch. So we have actually indexed SharePoint with ACLs and file systems and other S3 with ACLs into CloudSearch. And then on the other side, we've also got group expansion to do that group expansion. And I'll just throw in a plug for TwigKit. TwigKit also has some of the single sign-on and the user authentication part built in as part of that as well. So those tools are out there and available if you need to put that sort of application together.
Okay. Here's one for you, John. Are you able to handle bulk deletes for stale data or set data expiration?
So the way we handle deletes now is you send a delete for each document that you want to delete. So we don't have a notion of a delete query where you could specify a query that pulled a set of documents and then deleted those documents. You'd have to run that query and then generate the SDF for the deletes for all of those documents. But within that, we do handle document batching, so you can send a number of deletes at the same time within the same batch.
I'm going to throw in a thing here too. Unlike any other search engine I've ever done, you can access enormous results lists from CloudSearch. This is one of the things that just astonished me. Most other search engines will stop at like 1,000 or 4,000, but in CloudSearch I was able to download like 100,000, 500,000 doc IDs on a single query. It's like, whoa. And it comes back very quickly, like in a couple seconds. That's just kind of unheard of in the search engine world. So if you need these large deletes, it's actually really easy just to do a search, download them all, and then turn them around to the search engine. And we've done that for some of these larger batch deletes, and it works just fine.
Here's a question. Actually, there's a couple of questions with regards to what kind of documents can be indexes and sources. So one is, are there any connectors to CMS data? And in terms of document types, how do you handle PDFs or Word documents?
So out of the box, what CloudSearch has is a tool, a command line tool, that's also integrated into the console, which will do a very basic text extraction on PDF, Word, etc. What it won't do is any of the more complicated processing that Paul talked about to extract fields or to run regular expressions to figure out what the contents of the document are and how they should map to particular document fields. The tool we provide is really something that would just pull the entire content as a text blob and allow you to index over that. And again, I'll let Paul jump in here. I think, as we've seen, he's got a nice add-on there.
Yeah, our framework has that built in. I would just also say that Apache Tika is practically the standard way of doing that these days. Works great across a wide variety of sources, and it extracts both fielded data as well as the full text of the content. And it's really easy to use, so that's a great way to do it, is to integrate Apache Tika. So that's what we've done, and you can use our framework for that as well if you'd like.
Right. So here's a question regarding where the search UI, where the results and the UI need to be. The question is, does the search results UI need to be hosted on the Amazon AWS cloud, or can it be hosted on an in-house farm, CloudSearch?
Yeah, so I'll jump in on that one. So a little bit of the sort of CloudSearch architecture and design here. CloudSearch creates your domain for you in the cloud and then exposes 2 stable DNS entries for you to access the domain. So it's a RESTful service. When you're sending documents, it's a simple HTTP post. And as I mentioned, the security model is IP-based. So if any host on the internet can access that domain, provided that you set up the access control to allow it, and can post the document. Similarly, with search results, any IP address that you set up access for can send a GET request with the query and the URL to retrieve search results from your search domain.
Great. Here's one for data acquisition. Is there any way to pull data from a database by opening up a database connection to the source itself? Or does the transformation happen on CloudSearch itself? Or do I need to do the transformation from database?
So CloudSearch, again, out of the box, we provide the RESTful service that allows you to post SDF for your documents. And we don't, in the back, manage any kind of database connections or data transformation. And I really think Paul makes an excellent point that as you think about it, you want to put it into a search engine as a search document. That step is really for the developer to do themselves.
Okay. So we answered, I think, the question about how do you get from Solr to CloudSearch, but I've seen a few questions just popping up around why would you move from Solr to CloudSearch. In fact, one says, if it's working well and it doesn't need to scale, why would I go to CloudSearch? So I know we've heard feedback from some Solr users that when it comes to scaling, it becomes more difficult to manage and deploy as you go across charts and partitions and so on. So what have you been hearing, John?
Yeah, I mean, I think that Solr is well suited if you're willing to focus the time and attention and need the additional sort of ability to tweak and control at a very, very deep level, including writing code to do customized things. CloudSearch is really a great turnkey solution that takes a lot of the burden of figuring out deployments and partitioning and keeping your code up to date. One thing we haven't mentioned is that CloudSearch, it takes care of domain. So the operational overhead, really, of running your own search solution is really taken from your stakeholders. And company, I may not have, the desire to develop expertise in search to be able to deploy something like solar. I'd rather focus on my mission critical problem and put my effort behind that and just have search sort of out of the box, easy to use. So I think those are the benefits of going with CloudSearch.
There's also an availability story that some
Absolutely,
people are concerned about as well.
Yeah, if you're running your own solar deployment, then and a host goes down, then you have the headache of really you lose all of your data, you lose everything that was on that host. With CloudSearch, if a host goes out, we are able to reprovision and bring a host back up. In safe.
Other questions on your deployment here, your project. How many fields did you index per document, and how many of those were parametric?
Let's see. I'd say there are maybe a couple dozen fields. And by parametric fields, do they mean facet fields?
I don't have any more detail other than that.
if you mean facets, then there may be 4 or 5 facet fields. I think there may have been a few more that we selected as facets, but not necessarily actually used in the user interface. So maybe as many as 6 facet fields across the 24 fields or so. And then there was another maybe half dozen fields that hold numeric information that we use for relevancy scoring.
Paul, there was a question regarding relevance ranking, such as keyword weighting factors or even something like PageRank.
Yeah, PageRank is a perfect use for CloudSearch. If you have a PageRank that is some way of computing based on number of inbound links and authority references and things like that, what the PageRank is for each of your documents. I mean, most systems of any size will use like a Hadoop architecture for computing PageRanks. That's what Google does. And they do that as a pre-processing goes into the search engine, which you can then include into the rank expression. So it's a great way of doing document quality and using that in the ranking expression. Weighted keywords, there's a little bit you can do there. You can over-index some fields and get some weighted keywords on that. That's probably the best way to do it for now. And then I think there'll be some additional capabilities on weighted keywords in the near future.
Thanks, Paul.
Regions. So over the next year or so, you should expect to see more languages coming out with native support, especially Asian languages, which would support a native tokenization of that language, as well as stops and stems and synonyms for that.
Okay. Well, that's our time. Everyone, thank you for joining us. On your screen, you can see some contact information. If you have any questions, please get them to us. And there's a wealth of information on the aws.amazon.com/cloudsearch overview page. There you can get tutorials, demos, recorded, lots of information, FAQs, if you want more information on pricing. So please check that out. And in addition, obviously go to the Search Technology site. You can see Paul's blog on how he did it, as well as do your own Wikipedia searches. So thanks very much for joining us. Paul, thank you for participating. we look forward to working with you on the next webinars.
Thanks, everybody. It's been a real pleasure. And just to let everybody know, a recording of this webinar as well as the slides themselves will also be available.
Yeah, thanks for that reminder.